Hello grade 11s, this is a physical science lesson and my name is Gillian. Today we're going to look at the big ideas around redox reactions. Now, we have been busy with types of reactions. So we've already discussed reactions in aqueous solution. We've had a look at precipitation reactions, the ion exchange reactions. We've had a look at acid-base reactions. So now we're going to dive into the redox reactions, which are completely different to anything else we've come across. So let's have a look at the overview to see where it all fits in. So we have here our chemical types of reactions. And the first one we discussed were ions in aqueous solution. We discussed all these different types of reactions and we need to know those names. Then we had a look at our ion exchange, and that is where we have one ion bumping out another ion. So it's an ion exchange, and those were the precipitation reactions. And a precipitate is a solid which is formed. It is insoluble in aqueous solution, and so we see it as a solid. The other ones that we discussed were the acid-base reactions, and we spoke about the Bronsted-Lowry and Arrhenius theories and how to work out which one is which. Now, today, we're going to be discussing the redox reactions, and those are so completely different that you'll know that they're redox reactions because they involve an exchange of electrons. So, we have one substance that gives away its electrons, and in giving it away its electrons becomes more positive. The other substance takes on those electrons that have been given away and so becomes more negative. And so we're going to look at those in detail. Let's have a look then at the overview of the redox reactions and what we're going to delve into today. So, redox reactions. We need to know what oxidation numbers are and how to find them. And in so doing, we're going to have a brief look at the periodic table and how to use it. We normally get a periodic table in with our data sheets, and that periodic table, if you know how it works, is extremely useful. The other thing we need to then look at is the actual redox reactions and what does that encompass. And so redox reactions will have one half reaction of oxidation and another half reaction of reduction. We then speak about a reducing agent and an oxidizing agent. So these are all words, they're terminology that you need to understand and that you need to be able to write the definition of. The standard reduction potentials table is something we're going to look at in another lesson. It is also really important in writing balanced redox reactions, and so that we will look at in detail during our consolidation lesson, not today. Right, so let's have a look at the first big idea, which is oxidation number. Now, oxidation numbers are the numbers that are placed, they're called the unit oxidation number, that are placed above an element to show its charge. We have standard oxidation numbers. However, depending on what the element is reacting with, that can change. So it is very specific to the actual element, the unique element. So I have here on the board two atoms. You can see the one is lithium and the other one is sodium. Now, if we look at the periodic table, we will see that in our first group, we have lithium, that's lithium over there, and we have sodium there. Now, lithium, if we look carefully at the periodic table, has an atomic number, and that atomic number tells us, so if we look on this periodic table, it tells us there's the atomic number. That tells us how many protons we will find in the nucleus of the atom. If the atom is neutral, it's going to have the same number of electrons. So lithium has got 3. Its atomic number is 3. So you can see there it's got 3 protons in its nucleus and 3 electrons. Now, these atoms of the elements really want to have a good stable valency shell. In other words, the outermost shell of electrons, they want it to be stable. And you can see here that lithium has got 1 electron. Those electrons don't like to be on their own. They like to be paired. So what lithium is going to do, it's going to give its electron away. So it gives this electron away, and what happens? It becomes 1 electron less, and so the ion of lithium is lithium plus. It is a 1 plus ion. So if we look at sodium, now sodium is below lithium in the periodic table. Sodium is a little bit bigger, you can see there. Sodium has got a valence, it's got an atomic number of 11. I'm just going to put it above there. And so inside the nucleus, you'll see that I have actually put 11 protons in there. They're behind each other. And we will have 11 electrons. So let's have a look. 1, 2, I'll number them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But have a look at that number 11. That number 11 is all on its own on the outside, and it doesn't like being there because these electrons like to be paired, and so the atom is going to give that electron away so that it is in a more stable state. So this electron is given away. Guess what? It also becomes a positive charge. I'm going to write it down here. So sodium, sorry, not sodium. Yes, it is sodium. It's going to be sodium plus. It's going to have a 1 plus charge. That brings us to this first column, that going down in the periodic table. And the rule is that these metals, these group 1 metals, are going to give 1 electron away, and so they are going to have a valency of 1 plus. And we call that its oxidation number. Oxidation number. Let's have a look at group 2. So group 2, you can see there's beryllium and there's magnesium, one underneath each other. Beryllium has got an atomic number of 4. So I'm just going to change my pen so we can do this in a different color. Let's choose blue. And so beryllium is going to have 4 protons in its center, in its nucleus, and it's going to have another electron there in the outer shell. It doesn't like that. It's going to give both electrons away. So that electron and that electron are going to be given away. So beryllium likes to be 2 plus. Let's have a look at magnesium. Magnesium is 12. You can see it's below beryllium in the periodic table. And so it's going to, we need to add an extra proton there to the nucleus and an extra electron to the outer shell. Guess what? It also likes giving 2 away. It wants to be stable. So it gives 2 away. There's the one, there's the other, it gives it away. And so magnesium becomes 2 plus. So we can see that this group here, group 2, also likes giving electrons away, and their oxidation number is going to be 2 plus. What about, sorry, I just want to mention this, I've forgotten this, that when we have electron-rich atoms, elements, they will donate electrons. So an atom that has got lots of electrons is going to donate electrons, and it's going to become a positive charge. Now, the next lot, so you're going to say, okay, we've dealt with group 1 and group 2. What about those elements that fit into the other groups? And they are, I've taken an example of oxygen because oxygen is one that is electron poor, and so it draws electrons to itself. So let's have a look at oxygen. Oxygen sits here in group 6 of the periodic table, and it has got 16 protons and 16 electrons. Its atomic number is 16. So there are 16 protons in its nucleus and then I have drawn my own drawing of how these things all fit together, and I have represented the electrons as arrows. You can see I've represented them as arrows like that. Electrons like to be together. They spin in opposite directions so they can be together in an orbital, and so that's how I have shown it. It's just a drawing. It's not a perfect drawing. So here we have 1, 2 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now these two over here, you can see, are not paired, and the electrons like to be paired, and so oxygen generally is not going to give those two away. It's greedy, it wants electrons. So it wants to take on another 2 electrons, one to match that one there. I just need to erase this. I've drawn that incorrectly. So 1 to match this one, and 1 to match this one over here. So oxygen takes on 2 electrons, and so it becomes 2 minus. That is its oxidation number when it is involved in electron exchange. Now all these atoms, when they are pure atoms in their pure state, they will have an oxidation number of 0 because they're not involved yet in exchanging electrons. And so if we have oxygen on its own, it will have an oxidation number of 0. And we call that its unit oxidation number. Right, so each atom has a unique electron structure. We've seen that. So there are similar valency structures within the groups. So group 1, group 2, group 3, group 4, group 5, group 6. Those groups, group 7, it's not, I think it's also called group 17, those groups will all have similar structures in terms of how the electrons are positioned around the nucleus. So they will all react in a similar way. However, because of the difference of electrons, some will react more and some will react less. There are exceptions to this rule, to all these rules. So we have to be aware of those, and we will look at those after the break. We will see you then. Welcome back, grade 11s. We are talking about oxidation numbers. Oxidation numbers are really important in figuring out what's going on in a redox reaction, so we need to get this down pat. We need to understand it. We may not be asked it, but we need to be able to apply it in order to answer questions. So what we have seen is that because each atom is unique, it's going to give away a unique number of electrons or take on electrons. So it behaves in its own way. However, there are general similarities in behavior. And so if we look at the periodic table, we see that group 1 will behave, all the elements in group 1 will behave in a similar way. So on my screen here, we have the periodic table. So group 1 will generally give 1 electron away. So that gives 1 electron away, and it becomes a 1 plus ion. Group 2 is going to give 2 electrons away. So all the elements in group 2 will generally give 2 electrons away, and so those ions will become 2 plus ions. We've got group 3, and generally group 3 will give 3 electrons away, and so become a 3 plus ion. Group 4 is one of those groups that is does its own thing. It has its own rules, and so sometimes it will give 4 electrons away and sometimes it will take 4 electrons. So we're just going to leave group 4 for now. Group 5 generally take on electrons, and so they will become 3 minus. So they take on the electrons. Group 6 will take on 2 electrons and become 2 negative, and then group 7 or group 17 will take on 1 electron and become 1 minus. Now, there are definite exceptions to the rule, and I want to draw your attention before we flip to the next screen are these transition metals. So there are metals that sit here in the middle, the transition metals, and they also do their own thing. They are rebels, and they, depending on who they're reacting with, they will either take on electrons or give electrons away. So there are certain exceptions to the rule that need to be learned off by heart. So let's have a look at our exceptions. So we know now that oxygen, because it's in that particular group, that it generally takes on 2 electrons. However, in this exception, it does not. So let's look at it. I am going to get the unit oxidation number of hydrogen. Hydrogen is in group 1, and so generally it will have an oxidation unit number, a unit oxidation number of 1. There are 2 of them. So what does that mean? It means that we have got a +2 oxidation number on the hydrogens in this compound. Right. What does that mean? A compound or a molecule has to be neutral. Has to be neutral. The positives and the negatives that are joined together have to equal 0 for that compound or molecule to exist. So that means that this is 2 minus. But I have 2 oxygens. That means that 1 oxygen has got a charge of -1, or an unit oxidation number of -1. So this is an exception, because usually oxygen has got an oxidation number of 2 minus. Right. H as a hydride also acts a bit weirdly. So here we have this compound with us. Sodium is in group 1. So it's going to have a charge of +1. Its unit oxidation number is +1. So I'm going to put +1 down here. What does that mean on this side? It has to have, to balance this, it has to be -1. How interesting is that? So hydrogen in this case is -1. It's normally in group 1, and so it normally has a charge of, or a unit oxidation number of +1. But in this case, as a hydride, it is a -1. Now, let's have a look at our transition metals. Our transition metals, as I said before, depends on who they're with, whether they're going to give electrons or take electrons when they are in this reaction, in this bond. So let's have a look at manganese dioxide, because they're 2. Okay, so what I do is I normally put a line through there like that. I know that oxygen is going to have a unit oxidation number of 2 minus. What does that mean? I've got 2 oxygens, so 2 times 2 is going to be 4. So the negative charge here is -4. What does that mean? It means that manganese has to be on this side 4 plus, because manganese dioxide has to be a neutral substance. So I've only got 1 manganese, so I've got a unit oxidation number of 4 plus on the manganese. What about potassium permanganate? So I know if I draw a line here, I know that potassium is in group 1, and so it's going to give 1 electron away, and so its unit oxidation number is going to be +1. That means that this whole thing has to have, the permanganate ion has to have a charge of -1. Yes? I'm going to break that up. I'm going to write it over here so that we can see it more clearly. Okay. I'm going to draw my lines through. Oxygen, I know, has a unit oxidation number of 2-. There are 4 of them. So what does that make my overall negative charge? It's going to be 8-. Now, I know that this whole compound ion has to have an overall charge of -1, like that, -1. Okay, so what does that mean over here? What do I put in this space here? Well, what as positive will give me a -1 answer when added to -8? Well, that's going to be 7+. There are no other manganese there, so it's going to be 7+. Have a look at that. So in this compound or substance, manganese is 4+. In the permanganate ion, it is 7+. So you see, depending on what these substances are joined to, will give you the oxidation number. In other words, how many electrons it's taken up and how many electrons it's given away. We need to move on to what to do with these oxidation numbers. What do they actually help us do? They help us, they tell us what is going to be oxidized and how to write the oxidation half reaction and what is going to be reduced. Now, those are big numbers and big words. Sorry, big words. So redox reactions are made up of 2 half reactions, and you can see it in the name, red and ox. So the red stands for reduction, and the ox stands for oxidation. What does that mean? It means that we've got 2 half reactions. It's about electron transfer. We have got something which takes on an electron and something that gives away an electron. This happens at the same time. It's simultaneously. So the thing that gives away the electron will donate it to the thing that takes up the electron. And we've got special terminology for that. So oxidation is where the substance gives away the electron. It's a loss of electrons. So we have something like this, oil, which helps us remember. So a loss of electrons or oxidation is loss, is what this oil stands for. Oxidation is loss. Oxidation is the word that you need to couple with loss of electrons. It becomes more positive. It becomes more positive. So its oxidation number increases. That's what happens when a substance is oxidized. What about that substance which is oxidized, goes through oxidation? It aids with reduction. That's the other half reaction. And so we say that it is a reducing agent. So the thing that is oxidized, that becomes more positive, its oxidation number increases, gives away electrons, that aids reduction and is called the reducing agent. So let's have a look at these equations that I've got out here. Zinc, remember, is it's a neutral pure substance, and so its unit oxidation number is 0. We have another one here, and that is hydrogen gas. So we can also put a 0 above hydrogen gas because it is a pure substance. Right, now I'm going to do my little thing above here. And the sulfate ion is something that I do need to know, and that is a 2- oxidation number. There's only one as this compound complex ion stands. There's only one of them. So that sulfate ion, SO4 2-, has got a charge of 2-. I have got a neutral substance here, so 2+ on that side. I've got 2 hydrogens, and so hydrogen is going to be 1+. That's its oxidation number. What about zinc? Zinc sulfate. So here we go, the sulfate ion is 2-. That means that that must be 2-, and it's a neutral substance, and so 2+, there's only one zinc, so zinc is 2+. What has happened here? Zinc oxidation number has become more positive. So goes from 0 to 2+. There we can see there. How many electrons has it given away to become 2 plus? It has to have given away 2 electrons. So I write it here like that, 2 electrons. Let's move on to the other half reaction, which is reduction. So reduction half reaction, obviously if the oxidation is giving electrons away and becoming more positive, an increase in oxidation number, then reduction means that there must be a decrease in oxidation number. And so this substance gains electrons and becomes more negative. By doing that, what is it doing? It's helping oxidation, and so it is called an oxidizing agent. Again, I've got my 2 reactions here. In the previous slide, we've already looked at the hydrogen, and so we can put in our charges straight away. Remember, the sulfate ion is 2 minus, 2 plus on this side because it's neutral. Hydrogen, there are 2 of them, and so there's 1 plus there. And over here, it becomes 0. What's happening? We have got hydrogen ion as a 1 plus ion, and it's becoming hydrogen gas with a unit oxidation number of 0. So it is taking on those 2 electrons that the zinc gave away. And so we say plus 2 electrons. How do we know it's plus 2? Because we have got here H2. Okay, so one hydrogen is going to take on 1 electron, and the second hydrogen is also going to take on that second electron. So there we have a balanced equation where the number of electrons given is the same as the number of electrons that is taken. So when we balance redox reactions, the number of electrons in that reaction has to be balanced. Number given equals number taken. Right, quickly, grade 11s. We have a few types of redox reactions. We have synthesis, which is where a new product is formed. We have displacement, and we'll come across that again, especially next year in grade 12. Positive ions swap out their negative ions. We've already looked at some of those. And then decomposition, which is where you take a single substance and it breaks up into 2 or 3 separate substances. Grade 11s, that's all we have time for today. Hope to see you at the consolidation lesson next time.